Thank you for the nice welcome, and I'm very happy to be here and to talk. Just tell me how long should be the talk, please?
Okay, you can share your slides.
Yeah, what's the time limit?
About 45 with QA.
Okay, great. Thank you. So, okay, so I'll just plan like this. Okay.
Okay.
All right. So thank you very much for inviting me to your seminar. And when I was asked to give a talk, I thought the best way is to just give you in this time some taste of what's our lab doing, and to give you some uh, maybe a little bit brief of the topics that we're dealing with in our lab. Let me just fix my screen. 1 second. One second. Okay. That's it. Sorry. Okay, I'm sorry. So I'll just go ahead. I will talk about a few works that have been performed in my lab by students that do graduate studies. Most of the work is interdisciplinary, so it's combining several fields and trying to bring some visual processing and computation to other domains, trying again to push the limits of visual computing and deep learning and computer graphics to other domains and other data. So most of the focus of my talk will be actually on the data modeling, and the part of deep learning and geometry processing would be just the outcome of this examination and analysis. The first work I want to show you is involving a collaboration with the archaeological department, where we tried to perform some kind of reconstruction and filtering to archaeological artifacts. And we call the paper Deep Segmentation of Corrupted Archaeological Artifacts. The idea was that many times in archaeology, where you go and capture some data, the data is heavily deteriorated. And just to take the yeah. Yeah. So it's hardly you can see anything, any details. So many times there are humans involved in the loop, and the humans try to figure out what they can see. And of course, it requires a lot of labor, manual and human labor. And not only that it costs time, it's also very long. So we thought about how can we incorporate deep learning neural networks in order to boost this process, to help archaeologists in this processing of archaeological artifacts. Here you can see, for example, a photograph of a stone. And on this stone, you see there's a drawing, an ancient drawing. And maybe if we use some kind of knowledge, of learning process, we help by providing some kind of segmentation. Of course, the segmentation is not 100% accurate because the data is very, very noisy, but it can help in the process. So we came with a network, which I will show shortly. Let me just go back a little in this story and tell you what this all archaeology about. 1 second. Okay, so archaeology involves in looking at visual information. Either it is drawings on stones, it's called petroglyphs, or it can be also drawings and letters that is written on some kind of papers, which is called palimpsests. And these drawings are very, very deteriorated. They're corrupted. They are corrupted either by nature. Yeah, so for example, storms, environment, and etc. deteriorates and corrupts this information, or by other people coming and painting over these findings and etc. And the problem is that we want to restore, we want to reconstruct the original information. Okay, so the goal is to come up with a correct, we call it a deep segmentation, that brings back the original information in form of a mask. This data is found in nature. It's raw data. It's not synthetic, as you can see here. We take some kind of hand-drawn wall art or drawing. You can see the two kinds of drawings here, two kinds of letters, one in Hebrew, one in Arabic, and we want to restore the information. If we focus down, if we zoom to more local places, it's hard to see what's there. You can see it's very hard even for human to find what is the correct mask. So we say that this data is very challenging. So if we use a lot of knowledge from previous analysis of humans, then we can make a neural network learn from previous information and to come up with predictions. And this is what we call deep segmentation. Yeah, our idea is to have some inputs in ancient walls or handwritten letters, and to bring from the noise the correct foreground mask. The mask is not accurate. It's not and it should not be, because there's a lot of noise, a lot of occlusions, a lot of corruption. But it should combine together two sources of information. One is the visual information, some hints of what's going on here. Yeah, we have some hints here and also here. And another information is the knowledge, is the previous data that the network saw, and based on this knowledge, it should boost the mask prediction. What's the architecture that we use? It's quite elaborate. A simple segmentation algorithm, a simple segmentation network was not sufficient here because the data is really too noisy. So we start with a simple unit standard that comes with some initial segmentation mask. But as you can see, this is either too blurry, it lacks some details like the ears and etc., the legs. So we combine it with two additional branches. One is a classifier that tries to help the mask to fit into some kind of known class of objects, shapes. And another branch here, the second branch is a GAN branch. It's an adversarial network that tries to make these predictions look realistic. I will talk a bit about these branches and the network. So the initial unit is an encoder decoder, quite classical. It has three losses. One is a binary cross entropy that tries to separate between different classes. So the classes here is the foreground, which would be white, and the background, which should be black. So we have here the foreground background classical problem, but then we have also additional losses that try to regularize and improve the prediction. One is the total variation, trying to make it into one mask so we don't have disconnected components. And another one is a regularization, which tries to make it unblurry, tries to make it a sharp black and white mask. Okay, the second part is a classifier, which has which is also it's also a classifier which tries to add some knowledge to the shape. So basically, what the classifier tries to do, it tries to say, I want a good enough mask so that I can say what class does it belong. So in a way, it tries to boost the prediction of the foreground background segmentation into known shapes. So it's not enough to give here a mask. The mask should be good in terms of its classification. So we have here classes, and I will talk about the classes soon. And we have here a class cross entropy loss, which we add to the overall loss of the network. The second branch here is a GAN. And the GAN is simply trying to look at a mask, the predicted mask. As you can see, this is the mask of the unit of the encoder-decoder, and tries to make it look realistic. Realistic means that it sees a lot of true masks, ground truth masks, and predicted masks, and the discriminator should say whether it's a true mask or a synthetic one. If it's a true mask, a mask that was made by a human, then it's good. If it discriminates between a synthetic mask that was predicted by the unit, then it's bad. So this is like an adversarial game that tries to boost the unit to make the masks look more and more realistic and more like it was made by a human, and not something that is an encoder-decoder output. It's not enough. We had to add some kind of augmentation. So one kind of augmentation was trying to add some noise to allow the GAN to generate better examples. So here, this is the unit output. Here is an animal, here is a person, and we simply cover some parts of the shapes, and the GAN is able to reconstruct it. This way, we boost the GAN convergence. The data set that we got is obtaining pairs of inputs. Here, there's a petroglyphs inputs and the masks that were created by humans. And same was the palimpsest, the handwriting dataset, where we have these inputs that are heavily corrupted and letters on letters and so on, and the true ground truth that is covered here. The data is very small, and we had to augment it. So the augmentation here included separation between the foreground ground truth and the background, and creating candidates of foregrounds, as you can see here, foreground paintings and backgrounds that then we blended together. So we take like photographs of walls together with photographs of petroglyphs of hand-drawn animals and persons, and we blend them together, the background and the foreground, to generate new and more inputs. For the palimpsests, it was harder because here we have not only one foreground and one background, we have here several foregrounds. We have several handwritten symbols that we need to separate. So we have three separations. One is the original, the initial letters that we try to reconstruct. Then we have some letters that are not needed, that we're not interested about, and the background. So we do a context-aware in painting, where we fill the background and the occluders, and also we do in painting in the foreground to have a smooth foreground, which then we can paint. So we have three layers: a background, some occluders, and the foreground, where we can paint together through some weighted blending to generate new data. So this is a very important step because it allowed us to come from very small data set. Here we start with 80, 10, in the hundreds of ground truth artifacts, both for the petroglyphs and the palimpsests, not more than hundreds. And we were able to get to thousands, nearly 10,000 in the petroglyphs and nearly 20,000 in the palimpsests, which is something that the networks could work with. And here you can see results of our reconstruction. So this is almost nearly invisible inputs. And here are the masks that we were able to predict. And it makes sense. It helps a lot to give an initial guess what's here. So this is for palimpsests. You can see there are several animals and persons with weapons. And same for the handwritten symbols. You can see this heavily occluded, heavily corrupted, and we're able to reconstruct the full shape of the symbol. We try to evaluate also quantitatively the results. So we look at several metrics, binary and the MSE and the mean intersection over union and F1 and the earth moving distance. And we can see that when we run our model on our data, we are almost as running on standard segmentation problems like COCO. You can see, of course, our data, since it's much more corrupted and noisy, it's below COCO, but not far away in all metrics. So this is quite a good result. We also ran some empirical user studies in order to see how useful our segmentation is. And of course, this is not a segmentation that always it's something that archaeologists or professionals are happy about. So in the majority of the evaluation, they said that the quality is good, is above negligible, and also the efficiency of helping in processing this data is quite good. We also did a more extensive user study evaluation where we gave we gave these results, these masks, to archaeologists and asked them to grade their quality. And we see that in the majority we are above above 5, above 4 and 5 in a grade of 1 to 10. And more importantly, we could see that our masks in general improve the processing time. So it helps the professionals in their processing. You see, blue is without our mask, initial mask, and red. Sorry, blue is together with our masks when the archaeologists used our mask as initial guess, and red is without. So we can see that in most of the majority of time, blue is below the red, which means that it helps. Okay, the next project that we worked on is completely different, and it tried to look on a semantic perception of shapes by humans. So the idea here is to try to learn how humans perform abstraction, shape abstraction, and understand shapes. So we call these projects One Sketch, learning high-level shape features from simple sketches, and it's from last year. And our inspiration was one-line sketches. So we looked at these representations of shapes that are done simply by drawing one sketch, one line. The idea is that you cannot raise your pen from the paper or your pen from your pad, and you have to draw something meaningful. And when we looked at these human sketches, these are all made by human, we could see that they're quite complex, and they can convey a lot of information and a lot of complex ideas, like flowers growing in a vase, some kind of a woman dancing with a lot of motion, and some kind of poses, animals, etc., with very few and very simple sketches, very abstract. Still, we can understand as humans what's going on here. And the idea is to explore this kind of abstraction and shape representation with computational model, a deep learning model. Okay. So what we try to do is to look at how people draw one-line sketches quickly and very compact. And so the idea is to have some kind of shapes, as you can see here, and to look at their high-level compact representation made by human, and try to learn what's going on here. So learning these representations is something that is quite challenging. It has to be coherent. So humans many times draw one shape very differently. You can see this car here. You can see 3 completely different representations. Same like the vase here, this lamp. You can see one human draw the top, one just the stick, the stand, and one maybe some kind of a curve that belongs to this headlamp, and so on. So it's a lot of variation, and we try to build a representation in using computational tools that it should be coherent, robust, and still convey the human statistics. So the paper that we wrote here and the research that we performed had several contributions. First of all, we created a data set. We are the first to build a benchmark that tries to summarize the variety of one sketches in a coherent, reliable way, corresponding to shapes, to known shapes. Then we build a neural representation of the space of sketches, which we called an embedding space of the one sketches. And based on this, and you can see the embedding here. So this is a visualization, a 2D visualization of how the embedding of sketches looks like, how it was positioned in space. And this embedding, I will show you shortly, is very interesting because it allows us to really understand shape abstraction and to go to perform tasks like image retrieval from very simple sketches. So it gives us a very high-level semantic representation of the shape space. How did we perform this? So the idea was to create a benchmark of sketches. As you can see here, you have a lot of sketches that describe. You see the top row is the sketches that were made by humans, and this belongs to the red row. They belong to the shapes that you can see in the middle row, the red row. And the idea is that these sketches are not only describing a shape, because then we will miss the abstraction, but they should be minimal in terms that they should be sufficiently differentiating between the shape that they describe and another shape. So we have a correct shape, or the shape that it belongs to, and a contrastive shape. Okay? And by doing this differentiation between a shape and its pair, we were able to focus only on meaningful semantic features. So it's not that we want to draw the exact shape. We don't want to draw all the details. We just want to focus on features that separate between one shape and another. And the pairs are random. The shapes are from ShapeNet. And the idea came to us from a game, a very known game called Pictionary, where people try to sketch very quickly and very simple some ideas, sometimes quite complex ideas. And this game is very successful. It's called Pictionary, and very famous and well known. And people love to play it, and it's quite successful. And actually, it shows that people with very, very simple sketches can really convey quite complex ideas. And we did the same. So we build an interface. You can see the interface here, where we show people three shapes you can see here, and they should draw a minimal sketch, a minimal stroke that separates this shape from the other two. That was the task. And the sketch should be minimal. It should not have too many lines and too many details. So you can see here, for example, here, if the user draw too many details, it was canceled. And it should be also sufficient that it should separate. So here, for example, you can see it's not enough. They look almost the same. So we canceled the line to show this lamp. Here, the drawing was enough because it also has these angles. Right? So again, so the sketching should be minimal. Here it's not minimal to separate this bicycle from the lamps. And here it should also be sufficient. It should be separate. So here this line was not sufficient because it didn't separate the two lamps. This one separated. So these are the two goals. Yes, minimal and sufficient. And then we also had the QA, where we did the symmetric task. We give the user a sketch that somebody draw, and we ask to guess this sketch to which of the three shapes it belongs. And this is a way to do QA, to do quality assurance. So we remove all the sketches that humans could not discover, could not distinguish, could not guess. So we look at all the sketches that receive more than 50% accuracy in the human task. Actually, our data was made quite good. We obtained 91% of the sketches that pass this quality rate. So we have a quite good data set. We also remove sketches that are too long or too detailed. So we ended up with a benchmark which holds something around 4,500 samples taken from 250 participants, each drawing average 8.8 sketches, and so on. And then after collecting this data, we moved to modeling the embedding space by using a triplet Siamese network. The triplet Siamese network has three main branches, one for the sketch and two for the other images. One is the positive image that the sketch belongs to, and one is the negative image which the sketch should separate. Okay, and the Siamese networks are simply encoders that try to encode the three images into an embedding space such that the sketch and the positive image are close, and the sketch and the negative image are far away in the distance of the embedding space. We use a triplet loss. The triplet loss simply measures the Euclidean distance between images, between the sketched image in the embedding space and the positive, and the sketched image in the embedding space and the negative. And this distance should be as big as possible. We try to maximize this distance. Then in the selection test, we're given two images and the sketch, and we simply take the maximal between the difference when image number one is positive and image number two is negative, or image number one is negative and image number two is positive in the branches. And we simply select the positive image that gives the highest of this term. Okay, so this is the result. Okay, we take a sketch, we take a pair of images, we feed it to the network, and we take the one pair that gives the maximal grade. So here, this is the middle row where we take, these are the images that maximize the loss, the triplet loss. We perform pre-training by training the image branches with ImageNet and the sketch branch with Sketchy, just to get features that belong to images and to sketches. We do augmentation by rotating, translating the sketches in order to allow some kind of some invariance to position. Okay, I will move away from these details. And then we can see that the embeddings gives quite interesting features. We see that by taking the 2048 dimension space to a visualization of 2-dimension, we can see that shapes are grouped semantically, not by similarity, by shape similarity, but rather by features. You can see, for example, in this cluster here, that the similarity is more about some roundness of shapes, some curved shapes, while the top cluster here, you can see they're more like 90 degrees angles, things that look like more CAD, furniture, weapons, and etc. You can see that actually it belongs to what the people sketched. So you can see if we take some clusters, you can see here a cluster from the space, the embedding space. You can see that here are all belonging to sketches that are circular. Here are sketches that look like more like line sketches, and so on. we can see that the accuracy of the differentiation is quite similar to what humans do. So if you take now a sketch and two images and you feed it to the network in the testing step, we get results that are similar to the 91% that humans do in our experiment. So actually, we sometimes got even higher, but maybe this is an outlier, but overall, we are in the same range as, so the model that guesses the right shape from a sketch among a triplet is quite as at the peak of performance as humans. We also did some kind of robustness analysis by removing some part of the sketches, and we see that still the accuracy overall stayed high, meaning that compact sketches are quite expressive. They're good enough. So even if you cut 50% of a sketch, you still hold some information. So it means that we could also reduce more the task of writing sketches to get still a good embedding. We also applied the sketch paradigm to image retrieval, and we see that if we look at the number of sketches, so the color here are the number of sketches that we use. The more sketches you use to describe a shape, of course, you get better accuracy in the retrieval. Here, the K is the K top retrieved. So if we look at the K number one, is just we try to be as accurate as the best retrieved shape. And if we are more tolerant, we allow 3 or 4 or 5 up to 10 best retrieved shape. Then we see that our model can give one of the 10. Always we will get a retrieval that is one of the best 10 shapes that we can retrieve compared to other shape-based image retrieval. Of course, that the model has limitations. When the sketch is not significant enough, here we draw something that is circular. So we have something circular also in this cup, but also in the bicycle. So sometimes it will not be sufficiently separating. Sometimes the features that somebody draw, the sketch, was too high level, was too subtle, so it was like an outlier. For example, here is this X, it's a symbol on this remote. It does not have enough structural or geometrical information to be able to deal with. So it has to be something that it's relevant to the shape and not something that it's too high level. Okay, I still have maybe 5 minutes. I will show you one last work, totally different. So I'm trying to capture quite different ideas. Here, the work is called the Phi DNet, physical DNet ++, which is an enhanced physically constrained long-term video prediction. Is from 2022. And the idea here was that we want to look at videos and disentangle the physical partial derivatives that govern the physical motion. Sometimes there is physical motion in some videos with the visual details. And if we have the parameters of the video or the physical, we can then predict a lot of phenomena in these videos. So we look here at some specific videos that involve ball collisions and gravity, and also flocking, like crowds that go and follow some biological and physical laws. And we try to learn these trajectories, this physical trajectory. Here you can see this is a crowd, and this is a crowd simulation. And we try to extract the physical laws, the partial derivatives that govern these kind of crowding systems. And we also added a novel relative flow loss, we call it RF loss, which accounts for similarity in the dynamics of the video. Here is another example of ball collisions and from a billiard game. So we allow, by having this neural network, to capture both the visual and the physical terms separately, and then to perform even video manipulation. We can also, if we have the physical laws, we can also change the video. So we also some video manipulation. This is the neural network. It's based on an existing physical cell, which involves a Kalman filter on the partial derivatives that it tries to calculate. And this physical cell, again, it's not our contribution. It looks at the moment loss, some squared error, and some perceptual loss. And this is combined with an LSTM, convolutional LSTM, that tries to predict the next frame. So this is the disentanglement of the physical partial derivatives and the hidden states of the LSTM. The idea that helped us here was something that we used in order to measure the prediction of the next frame, and this is called the RF loss, okay, or relative flow loss. So standard optical flow loss looks at the trajectory of some objects in the video and tries to minimize the trajectory. So for example, here, it will look at this trajectory, the blue trajectory, and try to see how this blue trajectory is similar to the orange trajectory. In our loss, we said this is not enough, because sometimes these trajectories can move far, far away, and things can go really, really uncontrolled. So we try to create a loss between two frames, how one frame flows into another frame from at the same time. So this is a global similarity between the ground truth, this is G, and the predicted P. The idea is that if you look at the optical flow, then all these trajectories between the time steps 3 and 2 will look the same. These are the blue arrows. But if we look at the what's happening in the video, it's very far away. You can see these trajectories are actually far away. So we try to look at a more local frame-to-frame similarity. And here you can see some results of collisions, bouncing balls, some motions, and some crowd simulation that we are able to predict. We get quite high accuracy compared to state of the art. If we compare to in an ablation study, comparing to networks that do not use our architecture and our losses, we can see that our model is much more consistent and less blurry, as you can see here and here. This is the comparison. This is our result compared to a result of a network without using our formulation. You can see our is much more concise. Same for crowd. This is ground truth. This is our result, and this is a similar result without our components. You can see you have a lot of blur here. Here also things behave quite weird. We can also manipulate the motion. This is the original, and we can create new trajectories. Here is again a manipulation. This is the ground truth, and here is our result. You can see we can really manipulate how the motion looks like. Okay, I will not go into the ablation study due to the lack of time. Okay, in terms of conclusions, this work has some pros, which is that we are able to control and manipulate videos and really get the physical terms. On the downside is that we were not able to boost this to more complex physical scenarios, and this is a question that needs to be answered later on. So I will stop here. Thank you very much for listening, and of course I'll be happy to have some questions in the time